Before we look into something called a flux integral, we need to look at the orientation of a surface. And if we have what's called an oriented surface, it can be used to represent problems involving fluid flow. That's where the flux integral comes in. Keep in mind the fluid may be liquid or gas, which may behave as a fluid under certain conditions. A surface is called orientable if a unit normal vector n can be defined at every non-boundary point of S in such a way that the set of normal vectors varies continuously over all of S. If this is possible, then S is called an oriented surface. Note further that an orientable surface has two distinct sides, upper and lower if you want. Ellipsoids have inside and outside surface. Paraboloids, I don't know how I'd call that one. I guess we'd say the ones that are above the paraboloid and the surface is below the paraboloid. Planes have a top and a bottom, so they're orientable. Most surfaces we have ever studied are orientable, but here's one that's not. A Mobius strip is not, since it has only one side. I don't know if you've ever played with this. Take a strip of paper, cut it, twist one end one time only, and tape it together, and you have what's called a Mobius strip. And here's an example of a drawing. I actually can draw a Mobius strip with parametric surface here. But here it is. If you look at it carefully, you can see that you can draw a continuous line around the entire strip without removing your pencil. Hence, there is only one side to the surface. And here's the picture of it. Here's the parametric equations for it. I guess I could call it a vector value function if I want. R of uv equals 8 minus v sine of u cosine of 2u I plus 8 minus v sine of u sine of 2u j plus v cosine of u k, or something like that. But this is our one-sided surface. See, if I start drawing right here and draw a line on this surface, let me see if you can you see where that is? Let's see, this value is 0 and this value is maybe -5 or something like that. So if I start drawing this thing, here's my line going this way, going this way, going this way. Now you have to, now it gets weird, because it goes over to this side somehow, and here it is coming this way. Right there is the line still, right? And then that line, I'm still working on it. It's coming up along this side, and it comes back to the place where we started the darn thing, right there. So I drew one continuous line, never lifted my pencil. So that's not an orientable surface. So suppose we have a surface z equals g of xy. If we look at the function of three variables, capital G of xyz is z minus g of xy, minus whatever this is, we can orient the surface by use of the unit vector in the direction of the gradient vector, okay, at any point on the surface. So del G over the length of del G. So of course we have a two-sided surface. We would have an upper normal vector and also a lower normal vector, but that would just be the negative of that. So a simpler form might be for the negative one this, and for the positive one this. Those are both normal vectors. One's pushing in the positive direction from the surface, one's pushing in the negative. One's, we could say, the upper surface if you wanted, and the lower surface. So if a smooth surface F is given in parametric form by the vector valued function R of uv equals x of uvi plus y of uvj plus z of uvk, then unit normal vectors can be given by Ru cross Rv, that's the partial of R with respect to u cross the partial with respect to v divided by its length, or the negative of that divided by its length. Okay, the length being the same either way. And finding such normal vectors is required for what are called flux integrals.